monster. In this video, I am going to answer two basic questions that have been asked from me, and the number one is, I have discussed in last video about the design of a packed bed catalytic reactor, but I have not discussed the effect of diffusion on the rate coefficient, which has been discussed in this chapter number 18, homogeneous catalyzed solid reactions, Octave Levinos-Pyle book, Chemical Reaction Engineering. So in this chapter, if you have like I have discussed for my design of the acetylenizer reactor, case in which the catalyst with no diffusion or that catalyst is non-porous. But if you have a case where you have a catalyst with porous surface and it has some kind of diffusion, so you have to find the effective rate constant, because the reaction is actually taking place inside the catalyst pores also. So the change will be based on the Thiele modulus. The Thiele modulus is equal to the effective length multiply square root K rate constant. It is based on the different kind of units, so you will see the 1 dash based on kilogram and triple dash based on the volume of the catalyst. So by using this formula, we can found this term MT. MT is called the Thiele modulus. The Thiele modulus is used to found the effectiveness factor. Like in the no resistance to pore diffusion, you have low Thiele modulus you get from this equation, so there will be pure chemical reaction and there will be no pore diffusion. But if you get a higher Thiele modulus, in which the effectiveness of your rate constant decreases from 1 to a lesser value, so you have to accommodate the Thiele modulus. Like for example, my Thiele modulus from this equation MT, I got 10. And now we have to select what type of catalyst surface we have. We can have a flat plate type catalyst, cylinder type, or sphere type. Like it is 10, we will see from this, and we can check the effectiveness factor by moving along the x-axis. Like this is 0.1. This means due to the pore diffusion or diffusivity, your rate constant has been decreased to only 10%. It is the meaning of this Thiele modulus. And more of the mass transfer is taking place and less the reaction is taking place on the catalyst surface. So this is the answer of the first question. The second question that have been asked is, for example, you have multiple reactions like I have discussed, but the problem is that have been asked from me is W over F naught is equal to integral XA over minus RA. Minus RA is single. So if you have more than 2 or 3 main reactions and you want to put only one RA, so how you will find a cumulative or or the summation of those reaction kinetics? So I am giving the example of this Briggs-Haldane model for it is basically the model for the enzyme kinetics. But here I will discuss only two things. Like if you have a reaction in series, in the reaction in series you have to add the concentration. You can find the using the different kind of integral methods like Laplace transform and etc. You can find a single rate equation based on the series reaction. And if you have a parallel reaction in which there is only one component and it is reacting with different kinetics into 2 or more products, so you have to add all the reactions. Like if they are independent, for example, in one reaction, like I have N-hexane is going to butane, in the next reaction propane is going into another, for example, butane, like same. So both the reactants are independent, so I can find the volumes for the both those reactants individually. Like we can find from we can find W or V for the first reaction, and we can find the W or V for the second reaction, and then we can add, like we have W over F naught is equal to XA over R1 plus R2. We can add the both rates. If the rates are not independent, like there is only one reactant N-hexane and it is reacting to form butane, methane. A single reactant, N-hexane, is forming butane, hexane, methane, ethane. So these are not independent. The reactions are dependent as it has only one reactant. So I have to solve all the reaction kinetics simultaneously. You have to understand one important thing, that if you have a same kinetics for the production of different products, like I have N-hexane, it is in a single kinetics, in a single K, it is converting into ethane plus, for example, carbon dioxide plus water. So carbon dioxide and water are the part of that single kinetics or rate constant K. So it does not need any further to go into the confusion of defining different expression for that. But if it show different kinetics, like for example N-hexane goes to butane and N-hexane goes to water in another reaction, for example, it is rare to happen. So these are two different reactions and you have to solve them simultaneously. Like you have to found the R1, R2 and R3 simultaneously, and you have to set up a one fixed rate equation. So you can put in the design formula like W over Fa naught is equal to integral XA or minus RA effective. That RA is the solution of all the three kinetics. Like here, these are 2 to 3 reactions are taking place and they have found only a one rate, like Rp is equal to KRCES, this is equal to this. They have developed one effective expression for this, for the reactions that are not independent, that are dependent. So this is the answer of the second question, and this is enough for the question answer sessions related to the packed bed catalytic reactor. Thanks for joining us.